Hi everyone. So now let's get started with the projection matrix. So this is one topic which I can say that we have been waiting for, right? Because whatever we have studied till now was the foundation for projection matrix. Okay. So let's just start with this topic. So this is actually also written in the syllabus directly, which means that some topics sometimes they are not mentioned, but they are needed. But this is directly mentioned. Okay, so as you can see, this projection matrix is directly mentioned in the syllabus. So this projection matrix is a part of the syllabus, Gate D syllabus. Okay, so let's just get started again. Now we have seen that how to project a vector onto another vector, right? What we will do, we will take that vector and then we will take this vector also. This vector will represent by b minus p, right? Or b minus xa. And then we found out x as something like this. So p equal to, if you write ax, so p is just a multiple of a. So p equal to ax, if you write it, then it will be something like this, right? Now, what we want actually, see, we want this p equal to ax. We have got this right. So we would like to write this as a projection in terms of the projection matrix P, capital P. So which means what we actually want is that we want a matrix which is capital P, and we want to have that matrix, and then we will multiply with this matrix. Okay, some vector, let's suppose b, we will multiply this matrix with the vector b, and then we will directly get the projection. This is what our aim is. So basically if we want to project b, okay, b onto the subspace, the one dimensional subspace, then the projection matrix will look something like this. See, p equal to this much we have, right? Now what we will doing, we will be basically just rewriting it in that way, right? We will be just putting a bracket here and putting this b out. Okay, now you can easily see that I can rewrite this as p equal to capital P into b, where capital P is this quantity, right? This quantity. So uh so tell me, is this quantity that we have got, is this a vector, or this is a matrix, or what kind of quantity this is? Sorry, just tell me that capital P that we have got, is this a vector, a scalar, matrix? What kind of quantity this is? See, this A is a vector, right? So this is a vector, column vector, and then row. So basically, this particular thing is a matrix, right? This is a matrix of n cross n. And then this is a scalar. Okay. So this capital P is actually a matrix. Okay. This capital P is actually a matrix. Understood? So basically this capital P is a matrix which is computed like this. So what we have done, this is what we already knew, right? I'm just rewriting, okay? I'm just rewriting it in this way, and then I'm saying this capital P is nothing but this particular quantity. So basically the projection matrix that we are getting is this much. Okay? So the projection matrix that we are getting is this much. And it is a matrix, it is not a scalar, okay? This is a projection matrix. Understood? This is a projection matrix. Now, this projection matrix is currently that we have got, this projection matrix is basically projection matrix of some one dimensional space, right? Okay, so projection matrix of, I can say, 1D space, 1D space, 1D, okay, which is basically span of this, okay. This is a projection matrix of 1D space. Do you remember that we have also, seen one special projection matrix? I mean, the glimpse of the projection matrix we have seen, that was something U into U transpose, okay, where U was containing orthonormal basis. Okay, suppose you just contain, let's suppose the orthonormal basis, in the sense you just contain A only. Okay, which is a you can say orthogonal vector. Okay, orthonormal unit vector with the which is basically a unit vector, you can say. Okay, which is a unit vector. In that case, can you tell me what will be this P? This P will be this P will be A into A transpose. A, just let's suppose, I mean, okay, that is A into A transpose, and then A transpose into A is just one, right? So it will be A into A transpose, which is same as U into U transpose, because U into U transpose is also A into A transpose, right? So basically the earlier whatever we have seen, okay, you can say that that if you put, okay, if you put U equal to inside the U, if you put just one vector, then the earlier whatever we have seen is also the same thing. Okay. Anyway, we will relate much more things here, but for now I'm just telling you that earlier whatever we have seen is same as what we are seeing currently. Okay. So you can forget about the earlier things. Don't worry about it. But I hope that is fine, right? This is the projection matrix for 1D space. So now we know the projection matrix for 1D space. Now we also know the projection matrix of ND space, given that the space for the space we have the orthonormal basis, isn't it? Okay. Okay. Is this okay to everyone? Now, 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 what is our aim? See, let me just tell you that what we have, we know projection matrix of, we know projection matrix of n dimensional space also, but but given that we have orthonormal basis, right? Given that we have, now what we ultimately want to know, projection matrix of ND space for any arbitrary basis, right? So projection matrix of ND space for given any, right? Okay. By the way, let's suppose that I get some projection matrix. Maybe let's suppose I denote it by M. Okay. This is basically for any arbitrary basis. I mean, given that you have some arbitrary basis, that let's suppose you encode that arbitrary basis in A. Okay. I mean, A is a set of vectors which is containing the arbitrary basis. Let's suppose M is some, I don't know, maybe some formula A transpose A inverse A or whatever, right? M is some matrix which is basically getting computed using some arbitrary basis. Okay. Now let's take one more basis. Let's suppose U. U is the basis of the same vector space, but this is orthonormal basis. Okay. And then here I will be getting. Uh, so I mean I don't know the formula for now. Suppose, okay. But there will be some formula, right? Okay. And for you, I will be getting, what is the formula? For you, what I will be getting? U into U transpose, right? Okay. If it is orthonormal basis, then it is U into U transpose. If it is some arbitrary basis, then I will see the formula that we will be getting, right? Now, ultimately, do you guess one thing? Can you guess one thing? Ultimately, these two quantities will be same. Okay. Interestingly, these two quantities will be same, isn't it? Because the projection does not depend on the basis we are choosing. So interestingly, these two quantities, this quantity and this quantity, will be same. Is this fine to everyone? Okay. Now you know how to convert one basis to another basis. How to convert one basis to another basis? Do you know? Okay. So maybe we can do with the change of basis also, but let me just tell you with some other other interpretation, and then we can basically do with the change of basis also. But ultimately, whatever the formula that we will be getting, okay, whatever the formula we will be getting, let's suppose this is the formula, okay. I don't know what is the formula that we are going to get, but we will just drive in a minute. Okay, let's suppose this is a formula. This formula, and this formula, okay, matrix multiplication, all of these matrix multiplication and this formula will be same. What is the use of the projection matrix? Let's suppose P is a projection matrix. Then basically if you multiply this projection matrix to any vector B, then you will be getting the projection. Okay. This P be a projection, right? Let's suppose onto W. And what is this P? Capital P is a projection matrix for W. Okay. Let's suppose I calculate this capital P, okay, using basis B1, and let's suppose I calculate this capital P using basis B2. Will these different or these two quantities will be same? What do you think? These two will be actually same. Okay. These two will be same. It won't matter. It won't matter which basis we are using to compute this P. Ultimately, this P will look same. Okay. Because ultimately that PV has to be same because the projection is same irrespective of the basis that we are choosing. Okay. Anyway, so let's see some examples and then we will see for the higher dimension. For the single dimension, I hope you got the projection matrix. It is basically A transpose upon A transpose A. Okay, cool. So let's just solve this question. What they're saying, let S be the subspace of R3 spanned by this particular vector. Find the projection of B onto this S. Okay, they are saying find the projection, also find the projection matrix, find the projection matrix P that projects any vector onto this S. Okay, let's do step by step. Let's do this A. Okay, let's find the projection of B. So how to find the projection of B? Let's suppose this is A. So I think this is A transpose A transpose B into A, isn't it? Sorry, yeah, that is the case. So into A, so it will be the dot product of these two, 2 minus 3 plus 3, right? So I think this will be 2 upon 1 plus 1 square plus 1, 1 plus 1 plus 1. I think that will be 3, right? It is 3. 2 upon 3 into A. A is, let's suppose it is a column vector, doesn't matter. 1 minus 1, 1. Okay. Is this okay to everyone? Okay. 2 by 3 into 1 minus 1, 1. Um, so this is 2 minus 3, 3. So it is 2 by 1 square plus 1 square plus 1 square, 2 by 3 into 1 minus 1, 1. I think there is some calculation mistake here, probably. Okay, they are getting 2 by 3, 2 by 3, 2 by 3. This is 2 minus 3 plus 3. This is 2 by 3. Yeah, there is some calculation mistake. Okay, so it is actually minus of this. Okay. Anyway, so this is the answer, right? Now let's just see for B. Okay, let's just see for B. What is the answer we are getting? Find the projection matrix. Okay, now they're asking not just the projection, they're asking for the projection matrix, entire projection matrix. So let's just see how to calculate for this B. Okay, so what is the projection matrix? The projection matrix will be something into B, right? I mean, this will be in that form. If you want to project B, it will be something into B. So generally, like the idea is that we want to write it into this, we want to write this B at the end, right? See, this whole quantity is scalar, right? This whole quantity is scalar. So let's just write it, okay? Instead of x into a, let's just write it a into x. So basically, this is a into a transpose b upon a transpose a. And that is how we got our projection matrix, right? A transpose. So this is our projection matrix. Okay. So this P is coming out to be A is A is 1 minus 1 1 1 minus 1 1. A transpose A is just 3. So I think if you multiply these two, you will be getting the answer, right? So which means this will be uh, one of this. So let me multiply. Okay. It will be, I think, 3. So 1 by 3 into 1 minus 1 1 minus 1 1 1. Sorry, minus 1 1 minus 1 and 1 minus 1 1. This is the projection matrix that you're getting. Is this fine? Okay. Okay. So now what you can do, you can multiply this projection matrix just to verify. Okay. You can multiply this projection matrix into some vector. Okay. Let's suppose B. Just check. Obviously, you should be getting the same projection. But if you want, you can just verify this. Multiply this by B. Okay. You will be getting the same projection as this. What is B here? B is 2, 3, 3. So this is 2 minus 3, 3, 2, right? Minus 3 and 3. It is minus 2. It is 3 into 1 by 3, right? This is minus 2. Sorry, this is 2. This is 2. So 2 minus 2 and 2. Okay. So basically, you are getting the same projection. Obviously, you should be getting the same projection. This is just to verify. Okay. Cool. Now let's see this question. What they're saying. Let A be this matrix. Find the projection matrix PC onto the column space of A. See, till now we know only two kind of projection matrices. One is that if you want to project onto the single line, or if you want to project onto the space, then we should be knowing the orthogonal basis of that space, right? I mean, this is orthonormal. If you know the orthonormal basis, then we can directly do it, right? Okay. Now you just tell me that what will be the column space of A? Will it be multiple lines or just one single? This will be just single vector, right? You can take it as a single vector, right? Just 3, 4, a span of 3, 4. So this is a question where they are just saying that, okay, you take this span of 3, 4, and then find the projection matrix. I think you can do it, right? Okay. What about the projection matrix for PR onto the row space? In this case, do you have two independent rows? If there is one independent column, can you have two independent rows? Obviously it is not possible. So this and this must be multiple of each other. So I think it is multiplied by 4 by 3, right? Okay, so if you multiply by 4 by 3, so you will be getting this, right? These two has to multiple of each other. So that is why the projection matrix is just a space. You can find out the projection matrix for the span of, you can say, 3 6 6. Okay. So this is the question, and the answer is on the next page. It is easy, right? So you can find out A transpose and you can find out A transpose A. You divide both and then you will be getting, right? Similarly for B. Okay. It is easy question. I hope you understood, right? Now let's see this. Find the projection matrix P. I hope you can do it. This is just one line. Project the vector B1 and B2. Okay, you can do it. Find the errors equal to b1 minus pb1. You can also do this, right? Error means that vector. Okay. Which means if this is the space on which you are projecting, then this thing is actually called error also. Okay. Let's suppose it is B1. This is PB1, right? Understood? So these three things you can find out. Answer is on the next page. Okay. You can take this as an homework and then you can do it. Okay. Let's see this question. For every non-zero vector V, the matrix VV transpose is called the projection matrix. This is true or false? This is false, right? VV transpose upon V transpose V is projection matrix. Okay. So this is generally this will be false. Okay. But if it is unit vector, then it is true. Okay. In general, it is false. Okay. Now let's just see projection matrix for more than one dimensional subspace. Okay. If you have more than 1D subspace, then how to find out the projection matrix of that? It is also very, very easy. I mean, there is nothing fancy here. Let's just see this. We have the special case with us, but we now don't need the special case. Okay. For the special case, you can do it, right? We have done the practice also. For example, let's suppose this is the basis. Okay. Let's suppose this is the basis. This is orthonormal, right? And then you can basically find out the projection of this particular vector y onto this. How? You will be calculating UU transpose y, right? This is the answer. Okay. So I think for the special cases we have our answer, but let's see for the arbitrary basis. Okay. So suppose we have n vectors, right, in Rm. Assume that A's are linearly independent. Let's suppose this is the basis, right? This is the basis. Now we want to find the projection, okay, of B. In other words, we want to find some vector P, right? So this is B. Again, the same diagram. Okay. This is uh, the projection. Okay. You can say it is a PV, capital P into B, or you can just say it is a projection that we want to find out, right? So this projection will be basically the linear combination of these basis vectors. Is this okay to everyone? Right? Okay. Okay. So as you can see here, now let's just do one thing. Let's have, instead of writing it in this way, let's write it in this way. This is AX cap. Is this okay? You can write X, it doesn't really matter. Okay. If you want, you can write X. Doesn't really matter. Okay. This is AX. Okay. Cool. So basically, this is AX, right? The projection that we have is AX because it is a linear combination of all these vectors, right? And I'm assuming A is a matrix of all of these vectors. Okay. Now, now this AX that we have is basically something like this, right? Which means this is the projection. This projection is AX or AX cap. Okay, it doesn't matter. So this is E. Now the projection of P, projection P of B onto the line and onto the S equal to the column space of A. So basically, this will be in the column space of A. I mean, the projection will be obviously in the column space, right? And now this B minus, okay, this error, this is B minus AX cap is actually perpendicular to all the vectors here, isn't it? Last time also we did the same thing, right? So B minus AX cap is perpendicular to A1. You can write one thing that A1 is perpendicular to B minus AX cap. Okay. So actually, can anyone notice why I'm writing AX cap instead of AX? Can anyone, just think about it? The only reason is that No, not because of the unit vector or something. The only reason is that we want to be consistent with our notation. Do you remember that we always write system of linear equation as ax equal to b, right? So if I write ax here, then people will get confused. They will think that okay, ax and b are equal, so it should be cancelled out. Okay. So just to avoid the confusion, I'm writing ax cap. Okay. So basically, ax equal to b we used to write, but for the projection, I'm writing ax cap equal to b. Okay. Ax cap equal to b. Is this fine to everyone? So ax cap and p are same. P is a projection. X I was using for b actually. Okay. X I was using for b. By the way, I'm just asking you that suppose ax equal to b and b is not in the column space of a. Do you have the solution for ax equal to b? You actually don't have the solution. Okay. So we will see this later on. If you don't have the solution for x equal to b, then what we will do? Instead of solving for x equal to b, we will solve for ax cap equal to p. We will find the x cap, which means instead of solving for x equal to b, which because we can't solve it, but can we solve x cap equal to p? P is a projection of b and x cap is some coefficients. The projection of b onto this space, the column space, obviously, uh, I mean, this p will be obviously in the column space of a, right? So it always have the solution. So anyway, let's not get diverted from the topic. All the things will come slowly. So I was just telling you I'm writing x cap because I'm using p. If I have been using b, then I could have written x only. Okay, and because we generally let b ax equal to b, so don't get confused. These two can't get cancelled out. Okay, it's not like it is a zero vector or something. So this is projection p, which is nothing but ax cap, right? Why? Because this p will be some coefficient, some coefficients of this these a's. So that's why I'm writing ax cap. Now, just because of the definition of the projection, I can write a2 is also perpendicular to b minus ax cap. A3 is also perpendicular to b minus ax cap. Like that, right? Okay. Now you tell me if that is the case, right? If that is the case, then can you find out this x cap? Let's just see. Okay, let's just see, because ultimately I want to find out this x cap, that what are those coefficients. Once I get this x cap, can't you find this p? Obviously I will be writing the x cap and I will be getting the p, the projection, right? So this a1 a2 a3, all of this, I mean all of these vectors are perpendicular to this. Earlier also we did the same thing, right? U and b were perpendicular to that, right? So now also we are doing the same thing. So basically this a1 transpose into this b minus ax cap and all of this is zero. You can rewrite this in terms of matrix, right? This is a vector, b minus ax cap, this is a vector, this is also the vector, these two are the vectors. Now what you can do, you can write all of this a's, right, into one matrix, that this is as you can see. I didn't get that. Could you try again? Okay. So this is basically a1 transpose a2 transpose, all of this you can write in the compact form, right? So this is a vector, the dot product of two vectors. This is a dot product of two vectors. If you write this particular vector into this particular vector will be zero, right? So you're just writing in the compact form. Is this fine? This I have taken from Gilbert string. Now, what all you need to do is basically this is nothing but A transpose into the vector B minus AX cap. Okay. This is a zero vector, right? This is zero. This is a vector, this is a matrix. Okay. Now we want to find X cap. So what you will do, A transpose B equal to, or let me write in this way, A transpose A into X cap equal to A transpose B, right? Now, now to find the X cap, what you need to do, you can put this particular matrix here, which is basically A transpose A inverse into A transpose B. This is how you can find out the X cap. Okay. This is little complicated, but eventually you will understand that. So, what is our final aim? Our final aim to find out the P, right? P was the projection was AX cap actually. So, what is the projection now? So, what is the projection then? It will be AX cap, right? No, B is not in the space. So, the projection of B will be AX cap, which is nothing but A into A transpose A inverse A transpose B, right? If this is the projection, and if you want to write this projection into capital P into B form, okay, let's suppose this is small p, okay, the small p equal to this, then what is the capital P here? What we call the capital P? We call this capital P as a projection matrix, right? This is the projection matrix for any arbitrary basis that is encoded by A. Okay. So these are involving the three steps. What are those three steps? Three steps is that first step is to find out the X cap. Second step is to find out the projection P. And the third step is to find out the projection matrix. Okay. Now, suppose this A is orthonormal matrix, which means let's suppose it is U. If it is orthonormal matrix, interestingly, for orthonormal matrices, okay, if it is, let's suppose, let me just tell you one interesting fact. Orthonormal matrix, which is rectangular, okay, which means let's suppose you have five vectors, oh sorry, three or maybe two vectors, three vectors, let's suppose in R5 which are perpendicular to each other. Let's suppose you have three vectors, okay. Okay, these are the three vectors in three orthonormal vectors, right? Or you can say this is the orthogonal or orthonormal matrix, right? Rectangular matrix. Let's suppose this is U. Can you tell me what is U transpose into U? See, if U is this, let's suppose this is U, which is U1, U2, U3, right? U transpose will be like this, right? So U transpose into U will be this is U1, this is U2, this is U3. If it is rectangular, okay, then U transpose U will be actually this into this actually one. Everywhere else it is zero. Okay. So this is identity matrix. Okay. U transpose U is actually identity matrix. Understood? Now, what about U transpose? Is this also identity? The answer is no, actually. Okay. U transpose is not identity. I mean, if it is a rectangular matrix, if it is not the rectangular matrix, then yes, actually, both are identity. But if it is U transpose, you can just try it out. Maybe just take this U, right? U transpose will be 1, all zeros, 0 1 0 0 0 0 0 1 0 0. Okay, this is 5 cross 3 matrix. This is 3 cross 5 matrix. Let's just check if it is identity. Okay, this is okay. This is fine. So if you multiply this row with this will be 1. This is 0. This is 0 0 0, right? Okay. Now let's just check other columns, other rows. This is, if you multiply these two, this is 0 1 0 0 0, I think, right? If you multiply this, then this is 0 0 1 0 0. And what about the rest columns? If you multiply this, or rest rows, all are zeros, right? All are zeros. Is this identity matrix? No, right? This is not identity matrix. So basically, this UU transpose is not identity matrix. Okay, U transpose U is identity matrix. So this is just one fact I would like to share. So here I was saying, let's suppose for arbitrary matrix you are getting this, right? Now suppose A equal to U, which means orthonormal matrix. Then what is the projection matrix? U into U transpose U inverse U transpose. Then what you are getting? UU transpose, isn't it? Isn't it the same thing that we have already got earlier, right? So let's just do one thing. Let's just reiterate this what we have done. Okay. So let me just quickly drive it. It's actually easy only, but still let's just do it again. See, what I want a projection, right? Let's suppose this is some space and I want to project my B onto this space, right? Let's suppose I want to do this. Then what will I do? See here, let's just assume. So this is the orthogonal projection. Okay. Let's just assume this is small p. Okay. The spaces, let's suppose, spanned by linearly independent vectors a1, a2 to an or whatever, right? Let's suppose this space is spanned by this. Okay. Then I want to find out this p. Okay. I assume that p will be looking like ax. Okay, I mean ax cap. I'm just writing x cap. Or I hope it is okay to you guys, right? Just x cap to differentiate that it is not ax equal to b kind of formula. Okay, that's the only reason, so that you don't get confused. Okay. Otherwise, if you don't want to keep this hat, then you can remove this hat. Okay, but let's just keep it. Okay, so that you don't get confused. So this is something that it is very obvious that obviously it will be in the form of ax cap. Now, this is the vector that we always taken help of, right? This is b minus ax cap. So this vector b minus ax cap will be perpendicular to a1 also. So this dot product is actually 0. Similarly, this dot product is actually 0, and so on. Let me know if there is any doubt till this point. Okay. Now, if that is the case, then you can do one thing. You can write all of this in the compact form. Okay. So let's just rewrite in the compact form, and then you will be getting, see, these are the vectors, right? And then this is just one vector. Okay. Just one vector, which is b minus ax cap. You multiply this by this, it will be a scalar 0, right? Again 0, again 0, like that, right? So you have actually made it in the compact form. Now, once you write it in the compact form, now you can again, argue that this is nothing but A transpose into b minus ax cap must be a zero vector, right? From here, x cap, or maybe you can write first this a transpose ax cap is actually a transpose b. Okay. Okay. Now, from here, you can find out the x cap. What is the x cap? X cap will be A transpose A inverse into A transpose B. So once you got the x cap, then what is the next step? Can you get the projection? Yes, right. So what is the projection? So from here, the projection P equal to Ax cap, which is nothing but A into A transpose A inverse into A transpose B. That is equal to, yeah, this is the projection that we have got, right? Now what you can do, you can just rewrite that into P into V form. So capital P, which is a projection matrix, this is the projection matrix that we have got. Now there are a couple of questions that are still, unanswered. One of the question is that how we can take inverse of this, right? Is this guaranteed to exist the inverse? Which means this A transpose A inverse is guaranteed to exist. This is the first question. And the second question is that, as Diksha is also asking, that can we open up this inverse? Okay. Can we open up this inverse? So obviously we can't open up. The only reason is that because A inverse doesn't need to exist, or A inverse needs to exist. See, A is a rectangle matrix, right? A may be rectangle matrix, basically need not to be the perfect square matrix, right? Because these are just n vectors. The number could be anything. Okay, so you can say it is a rectangle matrix. So A inverse might not be making any sense. So that is why you can't open up this inverse. If you open up this inverse, then it will be mass, right? It will be A inverse get cancelled, and A transpose inverse get cancelled, and it will be perfect B, right? I mean, you will be getting B. You will get confused at what is happening. So you can't open up this inverse. But before coming to this, can you tell me, does A transpose A inverse need to exist always? You might remember we have proved, okay, that uh, we have proved something. And what was that? Earlier we have proved that rank of A and rank of A transpose A inverse is same. Okay. Here also I have pasted that proof. You can read it out, but we have proved it. So if A is, let's suppose m by n matrix. Okay. Then rank of A is how much? If these are the n vectors, tell me. If these are the n independent vectors, then rank of A will be n, right? Okay, great. So, so rank of A is n actually, right? A transpose A is basically n by n matrix, and its rank and rank of A is same, right? Its rank and rank of A is same, isn't it? So that is why this A transpose is full rank matrix, right? It is n by n matrix, rank is n, so that is why inverse always exists. Okay, inverse always exists. If this is having, okay, if A is having a rank n, then A transpose A is having rank n. And when will A have rank n? Whenever A has, yeah, A has n linearly independent columns. Okay. If it is having actually basis, basis is definitely linearly independent. If it is m by n and it is having actually the basis, let's suppose m linearly independent columns, in that case, in that case, A transpose A inverse always exist. Okay. If it is containing the basis, then A transpose A inverse always exist. Why? Because A transpose A is n by n matrix. Its rank and A rank is same. Rank of A and rank of A transpose A is actually same. If this is having rank n, which means n linearly independent columns, then it will also have rank n, which means A transpose A inverse always exist. Okay. Why that is the case? Why both rank are same? We have given the proof earlier also. I think I have pasted it here also. Maybe somewhere. Yeah. This is the proof. You can read it out later. We have also proved it earlier also. Okay. So I have given the proof why A transpose is invertible. I've also written the proof again, but you can just read it out if you want to. Okay. I mean the proof we have already proved, so that's why I'm not proving it. Okay. So finally, the projection matrix for any arbitrarily basis that is given to me is coming out to be this, right? So how to, kind of remember it? You know AX equal to B, right? You know this. AX equal to B. I mean, let's suppose that's what we want to solve. Okay. But suppose we can't solve it because let's assume B is not in column space of A. Okay. Let's suppose we can't solve it. Okay. Assume. Then what we will do, we will be basically projecting this B. Okay. If B is not in the column space, then we will be projecting this B onto this space and we will be solving for this P. Okay. Which means we will be essentially solving for AX hat equal to P. Right. We actually want to solve for, let's suppose AX hat equal to P. Okay. So instead of solving this, we will be solving this. Is this fine to everyone? Right. So we will solve this. Now, okay. So basically, what I can say that we have got this equation also, right? We have got this equation A transpose A x cap equal to A transpose B. So we want to solve for x cap. So what we can say that instead of solving, okay, instead of solving Ax equal to B, what will we do? We will be solving A transpose A x cap equal to A transpose B. Okay. So basically, see this x cap is same. So we started from this, that we said like, okay, let's just project. Okay, let's just find out the projection, right? So the projection is actually Ax cap. Okay. So we will find out the projection, and the projection is Ax cap, right? And then we want to actually solve for this X cap. We want to know what is this X cap, which means what is the projection. So what we did, we basically said like, okay, this projection, if this is P, then this particular vector is perpendicular to all the vectors, right? A1, A2, like this, right? And then we have got our projected vector, which is Ax cap, which is this. Okay. Okay. Is this understood? And that is how we got our projection matrix. Okay. So now let's just do one thing. Maybe I can just show you some questions and then you can just try to solve them. So basically, this is kind of step one, that we have done this, right? We are saying that okay, we want to solve for this x cap. Okay. So this projection we have got ax cap, which is this. So A transpose ax cap equal to A transpose B. This is also called as, this is actually the popular equation. We will talk about it again in the linear regression. This is also called as normal equation. Okay, normal equation. We will talk about it later also. So I'm just telling you one name. This is called as normal equation. Okay. So this projection that we have got in the projection matrix is this. See here, this is a projection ax cap, and the x cap is coming out to be this. So the projection matrix is actually this. Okay. Now suppose this capital A is just a vector A. Okay, just a single vector A. In that case, A transpose A is just a scalar. Is this okay to everyone? Right? If it is a single vector, then what you can do, you can write it like this. This is A transpose upon A transpose A. This is scalar, so I'm writing it down. Okay, into B. Is this the same thing that we have seen earlier? If it is just one vector, right? The special case that we have seen, one more, which was A is just U, right? In that case, the projection matrix will be U into U transpose U inverse U transpose B. So this is identity, which is U transpose into B, U transpose, right? So this is also we have seen earlier. So basically, this is what you can say is the final matrix that we have with us. Okay, these were the special cases, right? These were the special cases. So the special cases, if you want, you can remember, but that's fine if you even if you don't remember. Okay, actually this special case, right, these are the special case, particularly this orthonormal special case is actually special. I mean, sometimes we directly need it. Okay, so that's why I'm just telling you, okay, directly. Okay. Now now suppose A, columns of A, let's suppose. Okay, and U is orthonormal, normal basis of same same vector space of W. Then is this true or false? A into A transpose A inverse A transpose, this is the formula, right? Yeah. Equal to U transpose. This is true or false? Tell me. This is actually true, right? This is true. I mean, you can take any basis. It doesn't really matter. Okay, you calculate the projection matrix. You calculate using this basis projection matrix. Both will be same, right? This is true. Even if you take any other basis, even if you take any other basis, the projection matrix will not change. Any basis you can take. Okay, is this fine to everyone? Okay, okay, right. So you can take any basis. Okay. So now let's just see this question. So what they're saying, the Gram-Schmidt method. Okay, let's not worry about that. What does this method does? I mean, how does it work? Let's not worry about it. But it will produce the orthonormal vectors. Given any basis, it can convert to the orthonormal. Okay, from the independent. Let's suppose from A1, A2, A3. This is some linearly independent vectors in R5, and then you have got Q1, Q2, Q3. So Q1, Q2, Q3 is orthonormal. Okay, put these vectors into the columns of 5A. So basically, this Q is orthonormal basis, A is some random basis. Okay, it is also the basis, but it is not orthonormal. Now they are saying, give us the formula for PQ and PA. So can you tell me what are the formulas for PQ and PA? PQ and PA onto the column space of. So basically, these are the projection matrices, right? So what is PQ? It is easy, right? QQ transpose. What is PA? PA is A into A transpose A inverse A transpose, right? Now they are saying that is PQ and P are equal. What is PQ times Q? What is determinant of PQ? Okay, just tell me, is PQ and P are equal? So let's just see the answer, right? So here this is PA, PQ is coming out to be QQ transpose. These both are actually equal, okay, because both the projection projects onto the same subspace. Okay, so basically this is very important to know that both the projection matrices are actually equal, right? This is the question from MIT. Okay, this is the question from MIT. Understood? That both the projection matrices are actually equal. It doesn't really matter that which basis you are using. Okay. Now let's just solve this question. If A is this and B is this, find X cap P and capital P. This is again from Gilbert string. So I think you can do it, right? If A is this matrix, B is this matrix, what is capital P? So should we start from X cap? Okay. So let me know how to calculate this X cap. By the way, can anyone tell me what is this X cap? Is this a projection or this is a projection? Tell me. X cap is a projection or P is a projection? P is a projection, right? So what is this X cap? Can I say coordinates of projection in the basis of? Is this okay? X cap is just the coordinates, right? Or maybe you can say, oh yeah, coordinates of P. Okay, coordinates of P. If you take with the basis of coordinates of P, right? If you take with the basis of these columns. Okay. So what you can do, you can basically solve this equation. This is A transpose A X cap equal to A transpose B, right? This is the equation you can solve to find out the X cap. Okay. So how you know how to solve system of linear equations, right? This is a matrix, this is a vector. So you know how to solve system of linear equations. Using that, you can solve it. So the X cap will be this 5 and minus 3. Once you have this, you can definitely find out the projection, which is A into X cap. This is the projection. Okay. And the projection matrix also they're asking, right? Second, the matrix P. Uh, P times Q is correctly gives the projection matrix is this, right? The determinant is this. This is G multiply A times A to reach P. Okay. So you can calculate this P also, the projection matrix, using this formula. The solution is also from the Gilbert string. Understood? So how to calculate this X cap? You can basically solve the equation, which was, I called that equation as normal equation. Okay. So what was that equation? A transpose A X cap equal to A transpose B. Okay. Using this, you can find out the X cap. If you forget this equation, then you can easily, drive this. How? You will say that, okay, if this is B, right, then this is B minus AX cap. So A transpose, I mean every of this vector is actually perpendicular, so that's why A transpose into B minus AX cap equal to actually 0. So A transpose AX cap equal to A transpose B. Okay. This equation is called normal equation. Okay. So you can calculate the X cap, and then once you get the X cap, you can also calculate P. What is P? AX cap, right? And the projection matrix formula also you know, right? So you can calculate all of this. So the projection matrix will be this. You can calculate this, and then you can get the answer. Okay. Now, as one of the student was asking that can we open up this inverse, right? Can we open up this inverse? Again, this is from Gilbert Stein. They've also taken care of this silly mistake. Okay. So this is kind of silly mistake. Why? Because A is rectangular matrix. So inverse need not exist. I mean, is not even defined basically, right? Okay. So if you try to open up this inverse, then what will happen? You may try to split this, and that will you make that mistake and then substitute that into P, and you will think that it is identity matrix, right? The edge is rectangular, it has no inverse. We cannot split this, right, into something like this in our experience. So whenever you have, so they are saying, whenever you have the rectangle matrix, a problem that involves the rectangle matrix always leads to A transpose A. When A has independent columns, A transpose A. See, when A has independent columns, A transpose A is always invertible. This fact is so crucial that we state it clearly and give it a proof. So in the next page, they have actually stated it clearly, and they have proved it. Okay, that A transpose A is invertible if and only if A has linearly independent columns. Okay. So let's just solve this. Compute the orthogonal projection of this vector onto the subspace U, which is having this basis. By the way, is this orthonormal basis? At least orthogonal is there, but you can divide with the length, and you will be getting the orthonormal basis, right? So if it is orthonormal basis, then you don't need this. If you want, you can do it, but you can directly use the formula. You transpose, right? Okay. Now let's just see this. Compute PV using PV is a basically the projection matrix. Using this formula, they want you to compute. I think you can do this also. Okay. Now let's just see orthogonal decomposition. You might already know this, but I'm just telling you again. Any vector x, you can write it. Okay, any vector x, you can write it into two summation of two vectors. One is that the projection of x onto this that space. Another is that perpendicular to x, right? So which means if you're writing, let's suppose b, then you can write it as b equal to p plus b minus p, right? Which is perpendicular to this space. This is b minus p. Is this fine? Okay. For the unique vectors, this and okay, that's fine. So actually, let me just show you the small demonstration also. Okay. So see here, this is let's suppose some vector x, right? Some vector x, which I'm writing as summation of two vectors. So this. is actually x, which is summation of xw and xw perpendicular. Okay, maybe. Okay, so these two vectors are actually perpendicular. So this x you can write it, I mean, any vector x you can write it xw and x plus xw perpendicular. Okay, is this fine? Okay, you can play it around. I mean, there are multiple visualizations available, so I just took one of them. Okay. Now, interestingly, this x, right? That let's suppose I want to project this x or b, whatever. I can write it as the projection px. This is this is in w. Is this okay to everyone? Now, this will be this will be the vector which is basically x minus px, right? X minus px. Or if you like to write as b, this is b, then this is pb, this is b minus pb, right? Something like this. Okay, this is b minus pb. Okay, okay. So, yeah, this P is a projection matrix. Okay. So if you're writing like this, then you can write Px plus B minus Px, right? Or maybe PB. So basically, you can write this X or B, whatever you like to call. Capital P, this B, if you like to write in B, then capital P, B, which means a projection of B onto some subspace plus B minus capital PB. Is this fine to everyone? Now, now this can be rewritten. Okay, this same thing can be rewritten as this. PB plus I minus P into B, right? This is a vector in space W. This is a vector which is in the space of W orthogonal, right? Okay. Now, if that is the case, then P is something which is taking B and then projecting onto W, right? This is a vector in W. This is a vector in W orthogonal. Then what can I say about this matrix I minus P? If P is a matrix which is taking B and then giving the projection in W, then what is I minus P? It is also the matrix which is taking B and then it is giving you the projection of B into the space which is orthogonal to B. Is this fine? If P is a matrix which is a projection matrix giving you the projection onto W, then I minus P is also the projection matrix which is giving you the projection onto W orthogonal, right? Because this vector is in W orthogonal because this vector I have decomposed into something into W plus something into W orthogonal, right? I mean, this is into W, this is in W orthogonal. At least this part is fine to everyone that this is in W by the definition of the projection. This is in W orthogonal, but again the definition of the projection because B minus PB is in the W orthogonal. Is this part fine? That this is in W and this is in W orthogonal? Let me know. Okay, great. So now, if this is in W, this is in W orthogonal, then I can say that if P is some matrix which is taking B and giving you in the W, then I minus P is some another matrix which is taking B, right? And giving you the vector, the projection of B into W orthogonal. Okay. So let's just note it down this fact, which is very important. If P is projection matrix for W, then it automatically mean that I minus P is projection matrix for Okay. Is this fine? Okay. Great. So this is one small fact that I just like to share. Right. Okay. So if you basically if you add these two, then you will be anyway getting identity, right? Okay. So the projection matrix has some properties that it is symmetric. If you again and again do the projection, you will be getting the same vector. Okay. So it is idempotent. If you add the projection matrix of P and the projection matrix of PV and the projection matrix of orthogonal to it, then you will be getting the identity. That's what we have just shown. And uniqueness for the subspace, which means it is unique for the given subspace. We can easily verify this, right, by adding these two. So P and I minus P, if you add, you will be getting I. It is very easy to verify. You can easily verify these two also by the formula. So, for example, if this is the formula, you take the transpose of this. Okay, you take the transpose of this, you will be getting the same thing. It is A and the transpose of this, right? So, as you might be knowing that A inverse whole transpose, you can definitely, commute it, which means this is same as A transpose inverse, right? So you can just took the transpose inside, take the transpose inside, it will be A transpose A, again inverse, and then it will be A transpose, right? So it is easy to verify that P transpose is this. And if you want, you can verify that P square and P are also same. Okay. So these properties are easy to verify. Okay. Anyway, these are just properties that I would like to just list down. Now let's just solve this question. What they're saying, find the projection matrix for S and find the projection matrix for S complement also. Okay. So this is one question. I think there are a couple of more questions. So do you want to solve these questions first? There are a few more interesting questions, right? Okay. So the only questions are remaining. Okay. So the projection matrix is actually complete. Only the few questions, right, are the remaining. So for example, specifically the question related to S complement. Okay. I mean, these are just easy questions only. You can just compute P and then you can do I minus P. Okay. Yeah. So this is actually one of the basic building block, this projection matrix, linear transformation, change of basis. These are the just few building blocks for any topic in machine learning. That's why we have spent so much time in this. Okay. Okay. So by the way, let's suppose some space is given to you. Okay. Some space W is given to you, right? Which means it is a span of, let's suppose, some vectors, right? Let's suppose W is given to you, which is a span of, okay. Let's take two vectors, for example. And someone asks you how to calculate this W transpose, W complement, okay, orthogonal complement, which is a span of which vectors. How to calculate this? What you can do, if let's suppose someone asks you, you can put these two vectors into A, right? You want to find out some space which is perpendicular to the column space, right? Which is perpendicular to the column space. Which means, what is the perpendicular to column space? Left null space. Basically, what you can do, you can put that into A and then find this is same as left null space of A, or maybe null space of A transpose. You can solve A transpose X equal to 0, and then you will be getting what is this W orthogonal. Okay. If someone asks you that given this W, find out W orthogonal. Understood how to do it? Okay. So for example, then W orthogonal will be, you put that into A, right? So basically, they are asking you a space orthogonal to column space of A, which is same as left null space of A, right? which is same as null space of A transpose. So if they ask you to find out what is this W orthogonal, then what you do? You just solve A transpose X equal to 0, right? Solution is spans W orthogonal. Okay. Is this fine to everyone? Okay. Suppose they ask you, right? Okay. So this is, I can say, this is the recipe to find W orthogonal. Understood? Okay. Okay. So this is the recipe to find out W complement, right? Let me know if there is any issue with this particular recipe. Okay. Okay. In case if they ask, right? Cool. So now there are few questions that you can definitely try as in homework. Okay, these are easy questions only. Solution is on the next page. Just try it out. Okay, just try all of these questions. The solution is on the next page. You should be able to understand all of these questions, right? And then tomorrow, if you want, we can also solve these questions in the class. Otherwise, that is fine. I mean, these are easy questions and solution is on the next page. Now, tomorrow we will be starting a new topic, right? So the projection matrix is complete. Now, we need to start a new topic, and we will be finishing this linear algebra as soon as possible. So most probably, next topic we can start either as partition matrix or maybe PCA. Okay, I will just let you know. Right? Okay. Thank you, everyone. Thank you so much. Take care. Bye bye.